The lava flows at night, a river of molten orange sliding down the dark Hawaiian slope with the patience of honey. Where it meets the ocean, steam rises in white plumes that glow against the starlit sky, and the rock hardens from brilliant orange to deep crimson to black in the space of seconds. Each pulse of magma emerges from the earth like a breath, slow and steady, as if the planet itself is exhaling something it has held deep inside for longer than we can imagine. Lie down now. Let your breathing match the rhythm of this flow, slow, unhurried, constant. Tonight's story is about a connection so hidden and so gradual that no human will ever witness it directly, yet it shapes the ground beneath every step we take. It's about how the metallic heart of our planet, thousands of kilometers below, is not entirely sealed away from the rocky world above. Over billions of years, material from Earth's iron core has been leaking upward through the mantle, carried in slow currents of hot rock, eventually arriving at the surface in places like Hawaii as volcanic stone. This leaking is not sudden or violent. It is gentle, exceedingly slow, part of a deep circulation that keeps Earth alive and ever-changing. Pull back now from the lava, away from the island, up through the atmosphere until Earth hangs in space before you, a sphere of blue oceans and white clouds, beautiful and serene. But imagine it sliced open like a layered cake, revealing what lies within. At the very outside is the crust, thin and brittle as eggshell, the only layer we ever touch. Below that stretches the mantle, a vast shell of rock that is solid yet flows like putty over millions of years, making up most of Earth's volume. And deeper still lies the core, an outer layer of liquid iron and nickel, churning and convecting, and at the very centre a solid sphere of metal under such immense pressure it cannot melt despite temperatures rivaling the surface of the sun. Heat escapes from this core and from the deep mantle over time, and that escaping heat drives slow convection. Imagine enormous currents of rock creeping through the mantle at speeds comparable to the growth of your fingernails. Hot rock rises, cools near the surface, then sinks again in a cycle that takes tens of millions of years to complete. The mantle is not quiet or static. It is a slow river system on a planetary scale, transporting heat and material in patterns that shape continents and ocean basins. Descend now into the mantle itself. Picture it not as empty darkness, but as a dimly glowing realm of dense rock under unimaginable pressure, lit from within by its own heat. In places, hotter rock gathers into columns and begins to rise, ascending through the surrounding mantle like a plume of warm air rising through cooler atmosphere. These are called mantle plumes, and they can persist for millions of years, feeding volcanic hotspots far from the edges of tectonic plates. Hawaii is one such place, a chain of volcanic islands built atop a plume that has been active for perhaps 40 million years or more. The motion here is almost imperceptibly slow. If you could watch the mantle in fast forward, you would see broad glowing streams rising and cooler currents sinking, everything moving with the grace of syrup poured through honey. A single loop of this convection, from deep mantle to near surface and back again, might take longer than the entire existence of humanity as a species. Think of it as the planet's deep, slow breathing. Hot rock rises like an inhale, cooler rock sinks like an exhale, over and over, in a rhythm measured not in seconds but in geological ages. Sink deeper now, down through the lower mantle, toward the very base of this rocky shell. At the boundary between mantle and core, about 2,900 kilometers below your feet, seismic waves reveal something strange. Two continent-sized regions where the rock behaves differently. These are called large low shear velocity provinces, or LLSVPs, and they sit like vast submerged mountains beneath Africa and the Pacific Ocean. Seismic waves slow down as they pass through these regions, suggesting the rock here is denser, hotter, or chemically distinct from the surrounding mantle. Scattered around their edges are smaller, ultra-dense patches called ultra-low-velocity zones, or ULVZs, where seismic waves slow even more dramatically. These structures are enormous. Each LLSVP is wider than a continent and hundreds of kilometers tall. They are perched right at the interface between the rocky mantle and the liquid metal core, like enormous basins or mountains at the floor of a planetary ocean. Scientists think they may be leftovers from Earth's earliest days, when the entire surface was covered in a magma ocean and the interior was still sorting itself into layers. Some of that molten rock, perhaps mixed with material diffusing from the newborn core, may have sunk to the base of the mantle and solidified there, creating these strange provinces that persist today. The Pacific LLSVP sits directly beneath the ocean where Hawaii's volcanic chain grows, and some of the ULVZs nest near its edges. The hotspot above may be anchored to these deep structures, drawing its heat and material from this hidden reservoir far below. Return briefly to the surface. Imagine a geologist's hand holding a piece of dark volcanic rock from Hawaii, its surface rough and glassy, tiny crystals catching the light. In laboratories, scientists have analysed rocks like this, searching for clues about where the magma came from. In recent years, they found something surprising: subtle anomalies in the isotopes of ruthenium, a precious metal that should mostly reside in Earth's core. The chemical signature of these Hawaiian rocks doesn't quite match the average mantle. Instead, it hints that some of the material has interacted with or originated near the core itself, thousands of kilometres below. Isotopes are variants of the same element, identical in chemistry but slightly different in mass. Over time, natural processes fractionate them in characteristic ways, leaving a fingerprint that reveals an element's history. By measuring isotope ratios with extreme precision, geochemists can infer where magma's ingredients came from. The ruthenium anomaly in Hawaiian basalt suggests the lava carries with it a faint trace of the core, as if something from the metallic deep has made its way upward through the mantle and surfaced in these volcanic rocks. The connection is tenuous, indirect, but it's there, a whisper from the planet's hidden heart. Follow that whisper downward now. Imagine riding a stylized mantle plume from the Hawaiian hotspot into the depths, past the magma chamber beneath the volcano, through the brittle upper mantle where earthquakes occur, into the lower mantle where pressure turns familiar minerals into strange dense forms. The plume appears as a broad column of slightly warmer rock, glowing faintly against the darker mantle around it, rising with the patience of continents drifting. This plume likely originates near the core mantle boundary, perhaps where a ULVZ or the edge of an LLSVP focuses heat and buoyancy into an upward current. The descent is like a slow elevator ride through layers of colour and texture. Crystals deform under mounting pressure, minerals rearrange their atoms into tighter structures, temperature climbs, and the sense of weight becomes overwhelming. Not violent, but immense, the weight of an entire planet pressing inward. The plume is not a violent jet of molten rock shooting upward. It is a patient, persistent stream of slightly hotter material making its way through the mantle over tens of millions of years, millimetre by millimetre, slower than the slowest glacier, yet unstoppable in its buoyancy. At last you arrive at the core mantle boundary, a thin, rough interface that separates two fundamentally different worlds. Above lies the mantle, solid rock that flows. Below lies the outer core, liquid metal in constant motion. Imagine it as a ragged coastline in total darkness, with ridges of dense LLSVP material rising like undersea mountains, and low-lying ULVZ ponds where partially molten rock has pooled. Just beneath this boundary, the outer core churns, a swirling ocean of liquid iron alloy, its convection generating the magnetic field that shields Earth's surface from solar radiation. Here, conditions are extreme but steady. Temperatures reach several thousand degrees Celsius, hot enough to vaporize any substance at the surface, yet the rock remains solid under pressures millions of times greater than atmospheric. The metal remains liquid, its atoms jostling and flowing in great convective rolls that twist magnetic field lines into complex patterns. This boundary is not a perfect seal. Over immense spans of time, light elements and trace metals can diffuse or leak from the core into the overlying mantle, subtly altering its chemistry and density. Picture it now in abstract. Coloured streams and glowing dots representing atoms crossing the core mantle boundary. The core and mantle are not perfectly isolated from each other. Models and geochemical evidence suggest a slow exchange of elements, silicon, oxygen, magnesium and trace metals, between the liquid iron of the core and the lowermost mantle rock. In Earth's youth, when a global magma ocean covered the surface and the interior was still molten, core material likely mixed into the base of the solidifying mantle. This early mixing prevented the planet from separating into rigid chemical layers and left a legacy of heterogeneity in the deep mantle that persists today. The leaking continues, though it is not really a leak in any dramatic sense. It is more like a drip, unimaginably slow but persistent over billions of years. Tiny contributions accumulate into noticeable differences in the chemistry of mantle regions and hotspot lavas. This deep mixing may be part of why Earth's mantle remains so active, and why the planet's evolution took a different path than more geologically stagnant worlds. Without this gradual exchange, the mantle might have stratified into chemically distinct layers that resist mixing, choking off the convection that drives plate tectonics and volcanic activity. Trace the path now from boundary to surface. Core-derived elements enter the lowermost mantle, perhaps diffusing into the dense rock of an LLSVP, or mixing into the partially molten material of a ULVZ. Over time, some of this altered rock becomes entrained in a rising mantle plume, carried upward by buoyancy. As the plume ascends and pressure decreases, parts of the rock begin to melt. These melts are less dense than the surrounding solid rock, so they separate and migrate upward, pooling in reservoirs in the upper mantle. Eventually they feed magma chambers beneath volcanoes and erupt as basaltic lava at hotspots like Hawaii or other ocean islands. Only a tiny fraction of the plume's deep chemical signature appears in each eruption, which is why sensitive isotope measurements are needed to detect it. But that fraction is enough to tell us that the material in these surface rocks has travelled from the core mantle boundary, a journey of nearly 3,000 kilometres upward through the planet's interior. The process is a kind of planetary circulation system. Old oceanic crust sinks at subduction zones, descending into the mantle where it is heated and transformed. Some of it may eventually reach the core mantle boundary, interact with the deep structures there, then resurface very slowly through plumes over millions of years. What sinks can eventually rise. What rises cools, hardens, and may one day sink again. The cycle continues, endlessly patient. Zoom out now to see the big picture. This deep recycling and mixing is not just an obscure detail of planetary science. It influences Earth's habitability in profound ways. The style of volcanism, the growth of continents, the release of gases to the atmosphere, the strength and stability of the magnetic field, all are shaped by how heat and material circulate through the deep interior. The peculiar structures at the base of the mantle, shaped in part by core-mantle interaction, may have helped keep Earth's interior dynamic enough to support long-term plate tectonics and a stable climate, both of which are essential for life. This is not about dramatic events or catastrophic upheavals, it is about slow balance. Too little internal activity, and a planet becomes geologically dead, its surface cold and unchanging, unable to recycle nutrients or regulate climate. Too much activity, and the surface might be too hostile for complex life to gain a foothold. Earth has found a middle path, a long steady rhythm where deep processes and surface environments gently co-evolve. The hidden circulation at the core mantle boundary is part of that rhythm, a quiet engine that has been running for billions of years and will continue long after we're gone. Consider the timescales involved. Imagine a time-lapse of Earth over billions of years, continents drifting across the surface like rafts on a slow current, ocean basins opening and closing, volcanic chains appearing and fading as plumes wax and wane. Core mantle exchange and plume cycles operate over tens to hundreds of millions of years. A single loop from core mantle boundary to surface and back might outlast entire species, whole mountain ranges rising and eroding away in the time it takes for one packet of deep material to complete its journey. Contrast this with human timescales, the decades of a lifetime, the centuries of recorded history. We move quickly through our days, measuring time in heartbeats and breaths, worrying about deadlines and appointments. The planet's deep machine is not hurried. It moves at a pace that makes our daily concerns seem very small and very brief, and there is something oddly comforting in that. While we focus on moments, Earth's hidden heart moves on a schedule closer to eternity, unconcerned with anything but its own slow turning. Return now to the surface, to where we began, a Hawaiian lava flow at night. Viewed from a little farther away, the molten rock glows softly in the darkness, a ribbon of orange light against black stone, clouds of steam rising where it meets the sea. Above, stars appear between drifting volcanic clouds, brilliant and cold against the night. Below, unseen, the plume continues to feed magma from deep within the mantle, carrying with it faint chemical echoes of the core mantle boundary. Somewhere far beneath your feet, at a frontier you will never see, the planet's metallic heart and rocky mantle are still exchanging material in tiny amounts. This exchange, invisible and infinitesimally slow, keeps Earth's interior lively and its surface ever-changing. It is a hidden heartbeat, a warm, steady engine pulsing, quietly through geological ages, content to keep turning while continents drift, oceans rise and fall, and species come and go. Picture that heartbeat now as your own breathing slows. Deep below, at the core mantle boundary, iron atoms diffuse into rock. Somewhere in the lower mantle a plume begins its long ascent, warmer than its surroundings by just a few degrees, but buoyant enough to rise. Over millions of years, it will carry deep material upward, eventually reaching the surface as lava in some distant volcanic field. The rocks that form will carry with them a faint signature of the core, a chemical whisper from the planet's centre, testifying to a connection that spans nearly the entire radius of the Earth. This is the story of the leaking core. Not a catastrophe or a crisis, but a gentle, persistent exchange that has been happening since the planet was young and will continue for billions of years to come. It is the story of how Earth's deepest interior and its surface are not separate but connected through slow circulation. How what seems solid and unchanging is actually moving and mixing on timescales beyond imagination, and how the ground beneath us is part of a vast living system that extends from the centre of the planet to the edge of space. Let that image settle in your mind. A warm, patient engine turning far below, moving rock and metal in a rhythm older than mountains, slower than erosion, steady as the stars. The lava flows at night, and somewhere deep in the earth, the core leaks its secrets upward, one atom at a time, while we sleep and dream, and the planet continues its ancient, unhurried work. And yet there is more to understand about this quiet exchange, more layers to the story that unfold when we linger in the deep places and let the scale of planetary time wash over us. The core mantle boundary is not merely a surface where two layers meet. It is a dynamic region, a zone of interaction where the properties of matter are pushed to their limits and where the physics of our everyday world no longer applies in familiar ways. Here, the distinction between solid and liquid becomes less clear, and the very concept of a boundary begins to blur into something more gradual, more nuanced. Think about the outer core for a moment. That vast ocean of liquid metal swirling in the darkness. It is not still. Convection currents driven by heat escaping from the solid inner core create flows that can reach speeds of kilometres per year. Glacially slow by the standards of water or air, but remarkably fast for the deep interior of a planet. These flows organise themselves into complex patterns, rising columns of hotter metal, sinking sheets of cooler metal, and vast rotating vortices that stretch from pole to pole. As the liquid iron moves, it carries with it magnetic field lines, stretching and twisting them in ways that sustain Earth's magnetic field through a process called the geodynamo. This magnetic field is not a minor detail. It extends far beyond the planet's surface, creating a protective bubble called the magnetosphere that deflects most of the charged particles streaming from the sun. Without it, Earth's atmosphere would be slowly stripped away by the solar wind, as happened to Mars billions of years ago. The magnetic field, generated by motion in the core, is part of what makes the surface habitable, and that motion, in turn, depends on heat flow across the core mantle boundary, which is influenced by the composition and structure of the lowermost mantle, the very region where core material may be leaking upward. The connection runs deeper still. The outer core is not pure iron. It contains lighter elements, perhaps sulfur, silicon, oxygen, carbon or hydrogen, that lower its density and melting point. Some of these light elements may have been incorporated when Earth formed, but others may continue to enter the core from the mantle, or leave the core for the mantle, through slow chemical reactions at the boundary. When iron in the outer core crystallizes onto the solid inner core, the light elements are excluded, making the surrounding liquid slightly less dense and causing it to rise. This process releases gravitational energy that helps drive the convection, adding to the thermal buoyancy from heat flow. In this way, the leaking of material across the core mantle boundary is intimately tied to the generation of Earth's magnetic field. A change in the rate of exchange, or in the composition of what is exchanged, could alter the vigour of core convection and thus the strength of the magnetic field. Over Earth's history, the magnetic field has varied in intensity and has even reversed its polarity many times, with north and south magnetic poles switching places. These reversals may be influenced by changes in the deep mantle, by the arrival or departure of subducted slabs at the core mantle boundary, or by shifts in the geometry of the LLSVPs. The deep interior and the magnetic shield that protects life at the surface are coupled in ways we're only beginning to understand. Consider also the heat itself, the energy that drives all of this motion. Earth's interior is hot for two main reasons. It retains primordial heat from the planet's violent formation, when countless collisions of smaller bodies released enormous amounts of energy, and it generates new heat through the radioactive decay of elements like uranium, thorium, and potassium scattered through the mantle and crust. This heat must escape, and it does so through a combination of conduction, atoms jostling their neighbours, and convection, the bulk motion of hot material rising and cool material sinking. In the mantle, convection dominates. The rock is solid on human timescales but flows over millions of years, transporting heat far more efficiently than conduction alone could. At the core mantle boundary, heat flows from the hot core into the cooler base of the mantle. The rate of this heat flow determines how vigorously the core convects, how fast the inner core grows, and how much power is available to sustain the magnetic field. But the rate of heat flow is not uniform across the boundary. The LLSVPs, with their unusual composition and thermal properties, may act as insulators, reducing heat flow in some regions while allowing it to be more vigorous in others. This patchwork of heat flow may organise the pattern of mantle plumes, concentrating them around the edges of the LLSVPs, which is indeed where many hotspots like Hawaii are found. The presence of the LLSVPs and ULVZs also raises questions about Earth's early history. When the planet was young, only a few 100 million years after its formation, a Mars-sized body called Theia is thought to have collided with the proto-Earth in a cataclysmic impact. This giant impact melted much of both bodies, ejecting a huge amount of material into orbit that eventually coalesced into the Moon, and leaving Earth with a deep magma ocean. For millions of years, the surface may have been entirely molten, glowing red-hot under a thick atmosphere of vaporized rock. As this magma ocean slowly cooled and solidified from the top down, denser minerals crystallized and sank, while lighter minerals formed a crust that floated. But the very bottom of the mantle, in contact with the core, may have remained partially molten for much longer. Some researchers believe the LLSVPs could be remnants of this ancient magma ocean, dense piles of crystallized rock that sank to the base of the mantle and have persisted for billions of years. If so, they are among the oldest structures in the planet, silent witnesses to an era when Earth's surface was a hellish landscape of molten rock under a sky filled with vapour. Others propose that the LLSVPs could be accumulations of subducted oceanic crust, the remains of ancient seafloor that has been pushed down into the mantle at convergent plate boundaries and has settled at the core mantle boundary because it is denser than the surrounding mantle. Over billions of years, enough of this material could have accumulated to form the enormous provinces we see today. Yet another possibility is that the LLSVPs are enriched in iron or other dense elements that leaked out of the core early in Earth's history, when the core mantle boundary was hotter and more chemically active than it is now. Each of these hypotheses paints a different picture of Earth's evolution, yet all agree on one point. The deep mantle is not a simple uniform layer, but a complex archive of the planet's history, storing information about ancient processes in its structure and composition. The ULVZs, those smaller and even denser patches at the base of the mantle, add another layer of mystery. Some may be partially molten, with temperatures just above the melting point of mantle rock at those extreme pressures. Others may be rich in iron, having accumulated metal that leaked from the core or that was delivered by subducted material enriched in iron oxides. The existence of these structures challenges our understanding of how planets work. On a simpler world, one without plate tectonics or vigorous mantle convection, the interior might stratify into neat chemical layers and remain that way for billions of years. But Earth's interior is stirred by convection. mixed by plumes and slabs, and enriched or depleted by exchange with the core. The result is a mantle that is heterogeneous on all scales, from the tiny variations in mineral composition within a single rock sample to the continent-sized LLSVPs at the base of the mantle. This heterogeneity is not chaos. It is a kind of order born from complexity, a record of processes operating over vastly different timescales and length scales. A packet of rock in the deep mantle may carry with it a memory of where it came from, whether it originated as oceanic crust formed at a mid-ocean ridge, whether it spent time near the core mantle boundary absorbing heat and trace elements, whether it was melted and resolidified in a plume. Geochemists, by analysing the isotopes in volcanic rocks, can begin to read this memory, tracing the pathways that material has taken through the mantle over hundreds of millions of years. The isotopes of ruthenium found in Hawaiian lavas are one such clue. Ruthenium is a siderophile element, meaning it has a strong affinity for iron and preferentially partitions into metal rather than rock. During Earth formation, as the core separated from the mantle, most of the ruthenium should have sunk into the core along with the iron. The mantle should be depleted in ruthenium, and what little remains should have a particular isotopic composition. But some Hawaiian lavas show isotopic ratios that suggest they contain ruthenium that behave differently, that came from a source with a different history, possibly one that interacted with the core. The signal is subtle, a shift of just a few parts per million in the ratio of different ruthenium isotopes, but it is measurable and consistent across multiple samples. It suggests that the Hawaiian plume is sampling a region of the mantle that has been enriched in core-derived material, perhaps through the slow leaking of elements across the core mantle boundary over billions of years. Other isotopic systems, tungsten, osmium, helium, tell similar stories, each adding a piece to the puzzle of how the deep mantle is connected to the core and how that connection manifests in surface volcanism. Helium is particularly interesting. The mantle contains two isotopes of helium, helium-3 and helium-4. Helium-4 is produced by radioactive decay of uranium and thorium, so it accumulates over time in the mantle and crust. Helium-3, on the other hand, is primordial. It was incorporated into Earth when the planet formed and has been slowly leaking out ever since. Volcanic gases from hotspots like Hawaii and Iceland contain higher ratios of helium-3 to helium-4 than gases from mid-ocean ridges, suggesting that hotspot plumes are tapping into deep, ancient reservoirs of mantle that have retained their primordial helium. This primordial helium must have been stored somewhere in the deep mantle, isolated from the vigorous mixing of the upper mantle for billions of years. The LLS are candidates for such storage. If they are indeed ancient structures, they could have preserved pockets of primordial mantle composition even as the rest of the mantle was stirred and homogenized by convection. When a plume rises from the edge of an LSVP, it brings with it a sample of this ancient material, releasing helium-3 that has not seen the surface since the planet was young. The same plume also carries heat, of course, and that heat is ultimately what drives the volcanism at the surface. But the heat itself has a history. Some of it is primordial, left over from Earth's formation, and some is generated by radioactive decay. The heat from the core adds to this, flowing outward through the mantle and eventually radiating into space. The rate at which Earth is losing heat has been debated for centuries, ever since Lord Kelvin attempted to calculate the age of the Earth by modelling how long it would take for a molten sphere to cool. Kelvin's estimate, based on conduction alone, was far too short, only tens of millions of years, because he did not account for convection or radioactive heating. Modern estimates, based on measurements of heat flow at the surface and models of mantle convection, suggest Earth is losing about 47 terawatts of heat, roughly the energy of 10,000 large power plants running continuously. Of this heat, perhaps 5 to 15 terawatts comes from the core, with the rest generated in the mantle and crust by radioactive decay. The core, despite being enormously hot, is gradually cooling as it loses heat to the mantle. This cooling causes the inner core to grow as iron crystallizes from the liquid outer core, releasing latent heat and light elements that drive further convection. The process is self-sustaining as long as there is heat to lose, and models suggest it will continue for billions of years, until the core has cooled to the point where convection ceases and the magnetic field dies. But the rate of core cooling depends on the thermal conductivity of the lowermost mantle. and this is where the LLSVPs and ULVs come back into the story. If these structures act as thermal blankets, insulating the core, they slow the rate of heat loss and prolong the life of the geodynamo. If they are more conductive, or if they are eroded away by mantle convection, the core cools faster. The future habitability of Earth, millions or billions of years from now, may depend in part on the stability and properties of these deep structures, on whether they persist or dissolve as the mantle continues to churn. There is also the question of symmetry. The two, LSVPs under Africa and the Pacific, are not identical. The African LSVP is taller and more dome-shaped, while the Pacific LSVP is broader and flatter. They differ in their seismic properties, suggesting differences in composition or temperature. Why should there be two rather than one or many? And why are they located where they are, under particular regions of the surface? These questions touch on the deepest mysteries of mantle dynamics. One possibility is that the locations of the LLSVPs are controlled by the pattern of subduction at the surface. Slabs of oceanic crust sink into the mantle at subduction zones, and over time these slabs may accumulate in certain regions of the deep mantle, building up piles of dense material. Computer models show that subduction patterns can organize themselves into long-lived configurations, with slabs preferentially sinking in some regions and avoiding others. The regions where slabs accumulate could become the LLSVPs, while the regions they avoid could become pathways for plumes to rise. This would create a kind of planetary scale circulation pattern. Slabs sink at convergent boundaries, descend through the mantle and pile up at the core mantle boundary in preferred locations. The piles act as anchors, around which the rest of the mantle flows. Plumes rise from the edges or tops of the piles, fed by heat from the core and carrying with them material that has been enriched by interaction with the core or with the subducted slabs. The plumes reach the surface at hotspots, feeding volcanoes that create island chains and flood basalts. Eventually, the volcanic rocks at these hotspots are carried away by plate tectonics, subducted, and sent back down into the mantle, completing the cycle. This cycle operates over hundreds of millions of years, but it is not a closed loop. Material is constantly exchanged between different reservoirs: the crust, the depleted upper mantle, the enriched deep mantle, transition zone, the LLSVPs, and the core. Some material may circulate rapidly, returning to the surface within a few 100 million years. Other material may become trapped in the deep mantle, isolated from the surface for billions of years, and a small fraction may exchange with the core, carrying trace elements back and forth across the core mantle boundary over the entire age of the Earth. The result is a mantle that is neither well mixed nor perfectly layered, but something in between, a marble cake of compositions, temperatures and histories, stirred but not homogenized, retaining memory of the past while constantly evolving. This is the mantle that feeds the volcanoes we see at the surface, and it is why volcanic rocks are so diverse in their chemistry and isotopic composition. Each volcano is sampling a different part of this heterogeneous mantle, and by studying the rocks carefully, we can begin to map the mantle's internal structure and trace the pathways of material circulation. The implications extend beyond geology. The gases released by volcanoes, water vapour, carbon dioxide, sulfur dioxide, and many others, have shaped Earth's atmosphere and climate over billions of years. The early atmosphere was likely dominated by gases outgassed from the interior, with oxygen only becoming abundant after photosynthetic life evolved and began producing it as a waste product. Even today, volcanic outgassing plays a role in the carbon cycle, releasing carbon dioxide that would otherwise be locked away in subducted carbonate rocks. Over millions of years, the balance between volcanic outgassing and the removal of carbon dioxide by weathering and subduction helps regulate Earth's climate, keeping it within a range that allows liquid water to exist at the surface. This regulation is not perfect. Earth has experienced ice ages and hothouse periods, but it has been remarkably stable compared to other planets. Venus, with a thick carbon dioxide atmosphere and surface temperatures hot enough to melt lead, may have lost its oceans early in its history due to a runaway greenhouse effect. Mars, with a thin atmosphere and a cold, dry surface, may have lost much of its atmosphere to space after its magnetic field shut down. Earth, by contrast, has maintained liquid water at its surface for at least 3.5 billion years, perhaps longer, allowing life to originate and evolve into the complex biosphere we see today. The deep circulation of the mantle, the exchange of material with the core, the generation of the magnetic field, the release of gases through volcanism, all of these processes are interconnected, forming a planetary system that has sustained habitability over immense spans of time. And at the heart of this system, literally, is the core mantle boundary, where heat and material flow between the metallic heart of the planet and the rocky shell that surrounds it. Imagine returning once more to that boundary, to the ragged interface in the deep darkness. Iron atoms vibrating with thermal energy occasionally break free from the liquid metal of the outer core and diffuse into the overlying rock. Silicon or oxygen atoms from the mantle dissolve into the liquid core. The exchange is reciprocal, driven by differences in chemical potential and temperature, governed by the laws of thermodynamics operating at conditions we can only approximate in laboratories. Over billions of years, the cumulative effect of this exchange is to blur the distinction between core and mantle, to create a transition zone enriched in both rock-forming and metal-forming elements, a hybrid region that belongs fully to neither realm. This transition zone may be where the ULVs reside, patches of rock that are unusually rich in iron or partially molten due to the presence of core-derived elements that lower the melting point. Seismic waves struggle to pass through these zones, slowing down and scattering in ways that reveal their presence but leave their detailed structure uncertain. They are thin, perhaps only a few tens of kilometers thick, but they are dense enough to affect the dynamics of the core mantle boundary, perhaps influencing where plumes nucleate or where heat flow is concentrated. Plumes rising from the boundary may entrain some of this material, carrying it upward as they ascend through the mantle. The journey is long and the conditions change dramatically along the way. Pressure drops by more than 1 million atmospheres, temperature decreases by over 1,000 degrees, and minerals transform from one crystal structure to another as they pass through different stability fields. The plume material partially melts as it rises, with the melt fraction increasing as pressure drops and volatile elements like water or carbon dioxide, if present, lower the melting temperature further. By the time the plume reaches the base of the lithosphere, the rigid outer shell of the Earth, it has been transformed. What began as solid rock at the core mantle boundary is now a mixture of solid crystals and liquid melt, with the melt enriched in elements that preferentially enter the liquid phase. This melt is buoyant, less dense than the surrounding solid rock, so it segregates and rises, percolating through the matrix of crystals like water rising through a sponge. It collects in magma chambers beneath volcanoes, where it may reside for thousands or millions of years, slowly crystallizing and evolving in composition before finally erupting at the surface. The eruption itself is a release, a sudden opening of a pathway from the deep interior to the surface. Magma rises through fractures in the crust, driven by the pressure of dissolved gases expanding as pressure decreases. At the surface, lava pours out, glowing and incandescent, cooling in the air or ocean water. Gases bubble out, forming clouds of steam and volcanic fumes, and the rock, once it solidifies, becomes part of the crust, a new addition to the skin of the planet, but carrying within it a chemical memory of its long journey from the deep mantle, perhaps from the very edge of the core. This is how the core's secrets reach the surface, not directly, but through a long chain of processes, each transforming the material a little more, each adding its own signature. The geochemist, examining a hand sample of basalt, is reading a message written in isotopes and trace elements, a message that has travelled 3,000 kilometres and taken millions of years to arrive. The message is faint and fragmented, but it is there, testifying to the connectedness of the planet, to the way that the deepest interior and the thinnest surface layer are linked by the slow circulation of the mantle. And so the cycle continues, as it has for over 4 billion years and as it will for billions more. Slabs sink, plumes rise, the core cools and the mantle flows. Material moves between reservoirs, mixing and separating, enriched and depleted, carrying heat and elements and isotopes from one region to another. The surface is constantly renewed, old crust recycled into the interior and new crust generated by melting. The magnetic field flickers and reverses but persists, shielding the surface from the solar wind. The climate fluctuates but remains within bounds that allow liquid water and life. None of this happens quickly. A single human lifetime is far too short to observe the motion of the mantle or the drift of continents. But our species has existed long enough and developed the tools to see far enough that we can begin to perceive these slow processes, to measure their rates and trace their effects. We can send seismic waves through the planet and map its internal structure. We can measure isotopes with enough precision to detect the fingerprint of the core in a volcanic rock. We can build computer models of mantle convection and test them against observations. And piece by piece, we are assembling a picture of how the planet works, how its many parts interact, and how the system as a whole has sustained itself over deep time. The story of the leaking core is part of that larger picture. It tells us that the boundaries we draw on diagrams between crust and mantle, between mantle and core, are not absolute barriers but permeable interfaces across which material and energy flow. It tells us that the planet is not a static structure but a dynamic system, constantly evolving, its past inscribed in its present structure, its future shaped by processes that began billions of years ago and will continue long after our time. There is a deep comfort in understanding this, in seeing ourselves as brief witnesses to a system so much older and larger than we are. The lava flows in Hawaii tonight as it has flowed for millions of years and as it will continue to flow for millions more. The plume beneath the islands rises, fed by heat from the core mantle boundary, bringing with it traces of the planet's metallic heart. And deep below, in the total darkness, iron atoms continue their slow diffusion into rock, patient and persistent, contributing their tiny part to the grand circulation that keeps the planet alive. Let your mind rest on that image, the warm darkness of the deep interior, the slow upwelling of heat, the patient exchange of atoms across a boundary far below, and the eventual emergence of that deep material at the surface as glowing lava under the stars. It is all connected, all part of one vast planetary system, operating on timescales that dwarf our own, but proceeding with a regularity and persistence that is, in its way, deeply reassuring. The Earth abides, its hidden heart beating quietly through the ages, and we are here, for this brief moment, to marvel at its workings and to tell its story.